All right, for this problem, we're going to be looking at how we can use the percent composition of a compound to figure out the empirical formula for that compound. Now, empirical versus molecular formulas are only different in the fact that an empirical formula represents the simplest whole number ratios between the different elements that are in a compound, whereas the molecular formula represents the compound itself. So just as an example here, one of the previous problems on this worksheet dealt with benzene, which you may remember was C6H6. And so the molecular formula for benzene, the way it actually exists is that it has these 6 carbons and these 6 hydrogens. But if I'm talking about the empirical formula for benzene, the empirical formula simplifies the subscripts of the molecular formula so that they're all the smallest numbers they can be in terms of like the lowest common factor, or basically thinking about it as how you can divide all the subscripts by a number to get them to be the simplest whole number values. So for C6H6, that value we would divide by is 6 because we can divide both these subscripts by 6. And so we would just get CH for the empirical formula. And so you can notice that CH kind of represents the simplest whole number ratio between the elements. We have 1 carbon for every 1 hydrogen. Now we know in the molecule itself, there's 6 carbons for every 6 hydrogens, but you know, that ratio between the elements is 1 to 1. So that's what's being represented by the empirical formula. And one of the other things I talk about in the lecture on this topic is that you can have an empirical formula that has many different types of molecular formulas that all come back to the same empirical formula. So for example, what if we had C12H12 or C8H8, right? Those formulas, those molecular formulas, which would represent how that molecule actually exists, they all tie back to this exact same empirical formula. And so when we're asked to solve for the empirical formula of a compound, we want to recognize that that is going to come from just looking at the mole ratios between the elements in the compound. If we know that for every 1 mole of carbon, we should have 1 mole of hydrogen, then we can actually get that information by thinking about the mass percents. And so that is where mass percent is going to come into play here. Now we have to do a little bit of manipulation here to get the information we're going to need to be able to look at the whole number mole ratios. But once you know the process for this, it's not that bad. I want to point out for this problem and for the next few problems, we're going to be doing this same concept over and over again, but usually from a different starting point. And this problem, number 10, is the simplest because it starts with the mass percents of the elements that are in this compound. So we're being told we have a compound here that is 43.64% phosphorus and 56.36% oxygen. And the fact that we already know those mass percents saves us a lot of steps from a typical problem like you're going to see in number 11 and number 12. So the important thing to recognize when we have mass percents given to us is that how we're going to use these is we're first going to assume 100 grams of the compound so that we can use these mass percents as actual masses of each of those elements. So that would mean that the 43.64% phosphorus would give us 43.64 grams of phosphorus in 100 grams of the compound, right? So think about that, right? If you have 100 grams of the compound and 43.64% of that mass is phosphorus, then that means we just take the percentage as the mass in 100 grams of compound. So the whole reason we do this assume 100 grams is so that we can just use those percentages as masses, right? It just makes things a lot simpler. Now, to get the empirical formula, I can't compare the masses of the two elements. I want to compare the number of moles of the two elements. So I'm simply going to take this 43.64 grams of phosphorus and convert it into moles using the molar mass of phosphorus, which you just look up in the periodic table, this 30.97 grams, and we're dividing by that to get the number of moles. So this number of moles that we're getting over here on the side here, this is the number of moles in 100 grams of the compound. So we're going to do the exact same thing with the oxygen. The oxygen has 56.36% by mass for this compound. So we're taking that percent as the mass of oxygen in 100 grams of the compound. And we're doing the exact same thing we did with the phosphorus. We're converting this into moles by dividing by the molar mass of oxygen, which you just get from a periodic table. Again, the value we're getting here at the end is the number of moles of that element in 100 grams of the compound. Now notice, in order for us to compare the number of moles of each of these elements, they have to be the number of moles in the same total amount of compound. You can't compare moles if you have different amounts of the compound. And that's going to be something that's important as we shift to problem 11 and problem 12. But just note here, right, that these two number of moles, they're referenced back to this same 100 grams of compound, the same amount of the compound as a whole. And that's important because they need to be coming from the same amount in order for us to compare them and actually see what their ratio is going to be. Now, when solving for the ratio between these two, I always like to identify the number that is smallest, and I always divide by the smallest number. That kind of makes sure that you get something for your ratio value, for your answer, which down here you'll notice we're going to get 2.5. But it gets you something that's usually easier to figure out how to make into a whole number. Because keep in mind, again, these empirical formulas need to represent the whole number ratios, the simplest whole number ratios between the elements. And so you'll notice here the ratio we're taking of these two sets of moles, right? How many moles of oxygen do we have per mole of phosphorus? Well, we're taking the number of moles of oxygen, we're dividing it by the number of moles of phosphorus. And so this 2.5, let's keep in mind what this means, right? This 2.5 means that you have 2.5 moles of oxygen per every 1 mole of phosphorus, right? So if I was going to write out my formula right now for what this would look like, then I would use these numbers, 2.5 and 1, as my subscripts in the molecular formula. So I'm going to start with phosphorus here, just because I have the intuition of knowing that, normally we put phosphorus before we put oxygen in a molecular formula. But for you guys, as an answer, it would be fine if you put oxygen before phosphorus. I'm not going to penalize you for that. So just keep that in mind. At this point, with these molecular formulas or empirical formulas, I'm not going to pay particular attention to the order in which you put the elements. But what is going to be important here is that you get the subscripts right. So based off this ratio that we just determined, we're basically saying that if there's 2.5 moles of oxygen for every 1 mole of phosphorus, then my formula is going to have a 1 for the phosphorus. So notice I could include that 1 there, but most of the time we don't bother if it's just a 1. So that's why I don't have it there. But it's kind of implied by the way that this is written. And then I'm putting the 2.5 moles of oxygen as the subscript for oxygen. But the tricky part about this is that empirical formulas have to have whole number integers only for their subscripts. So when you get to this point and we've got this 2.5, we know we're not done because we can't leave that as 2.5. We have to get that to a whole number. And the way that you get a 0.5 value to a whole number is to multiply by 2. So anytime you get a ratio with a 0.5 value or something very close to 0.5, this could be like 0.4999 or something like that, or even 0.489, something that's close to 0.5, you know that multiplying by 2 will get you to a whole number. So that is why I'm multiplying by 2 here, because I have this 0.5 value for the oxygen. But multiplying by 2, we want to multiply both subscripts by 2. So the phosphorus, the 1 that's implied here is going to get multiplied by 2 to become 2. And the 2.5 on the oxygen is getting multiplied by 2 to become 5. And so you'll notice now we have a formula where the subscripts are whole numbers. And so this would be our final empirical formula for this problem. We would have P2O5. Now we're also asked for the molecular formula, and if we go back up here, we'll notice we were also given what the molar mass is for this compound, that it's 283.3 grams per mole. So the way we get the molecular formula after we've determined the empirical formula is we first figure out what the mass is of the empirical formula. And I call this the empirical mass. And this is done the same way you would do a normal molar mass calculation. You just look at the formula and notice that there are 2 phosphorus. So I'm going to take 2 times the molar mass of phosphorus. There's 5 oxygen. So I'm going to take 5 times the molar mass of oxygen. And I'm going to add this all up to get my empirical mass. And then from there, we're going to compare the empirical mass to the molar mass. Because if we remember, from the way this empirical to molecular formula thing worked, we should have noted here that the molecular formula is always a whole number multiple of the empirical formula. So the molar mass of the molecular formula should also be a whole number multiple of the empirical mass. And so if we compare the molar mass to the empirical mass, we should get a roughly whole number ratio, which is then going to tell us how to multiply the empirical mass to get the how to multiply the empirical formula to get the molecular formula. It also would be how you would multiply the empirical mass to get the molar mass. But note here that the way you set this up every time will always be to put the molar mass that you're given over the empirical mass that you solved for from your empirical formula. And that your empirical mass should usually be less than your molar mass, or in the case where your empirical formula actually is your molecular formula, then these two numbers would match essentially, and you'd get a ratio of 1. And I can't remember, I might have an example of that coming up in the next problem. But keep in mind here that if you ever get an empirical mass that's larger than the molar mass you're being given, then that's usually a big tip-off that you probably made a mistake somewhere. Because you should always be getting an empirical mass that's either equal to or less than the molar mass. When I divide these two values for this problem, I am getting a factor of 2. And so that is telling me that the molecular formula for this compound is twice the empirical formula. So I simply take my empirical formula, P2O5, I multiply it by 2, so each subscript is going to get multiplied by 2 to get P4O10. And so this makes P4O10 my molecular formula for this compound. All right, so notice again, another way to double check your work at the end is to make sure that your empirical formula is a simplified version of the molecular formula. And you'll note here the molecular formula, the most we can simplify this is to divide both of these subscripts by 2 to get P2 and O5. P2O5, you could also, when you solve for that, double check that it makes sense that this is an empirical formula and that you can't simplify it any further. And so if you notice here, we can't divide 2 or 5 by the same number to get another set of whole numbers. So that means this is the simplest version of this this empirical formula or of this ratio between the elements. All right, I hope that was helpful for this problem. Again, this one is a little bit simpler than the next two, 11 and 12, because this one starts off with the mass percents given to you. So you get to jump right into assuming 100 grams, solving for the number of moles, and then looking at the ratio of the moles to get that empirical formula. These next two problems, 11 and 12, are a little bit more involved in order to get to that point where we can actually compare the moles.